Okay, so why do things move part 2? This is all about Newton's second law. We talked about the first law, which just said basically everything is going to continue doing what it's already doing, absent of any forces. Now, Isaac Newton, when he figured that out, he also figured out that he needs to sort of define, or at least he discovered the definition of how this works, okay? So first he realized that, well, if you don't have any forces, things are going to keep doing what they're doing. But he also realized that there is a mathematical formula which governs this, which happens to be one of the laws that nature plays by, and that is Newton's second law. And in there, okay, we also answered this question here, okay? That's a terrible circle because I'm on an angle, okay? We answer this question here, which is, what is the relationship between force, mass, and acceleration, okay? So what is the relationship between how hard you push, the mass of the object, and how fast it changes its speed? Okay? All right, so Newton's second law. I'm going to give you many ways to say the same thing. Okay? First of all, this is the more mathematical yet linguistic way of saying it. The acceleration produced by a net force on an object is directly proportional to the magnitude of the net force, is in the same direction as the net force, and is inversely proportional to the mass of the object. Sounds like a mouthful, but if we break it down, it's actually pretty easy to understand. Okay? So, let's break it down. All right? Let's talk about this part, the acceleration. Okay? Remember, we're talking about the acceleration of an object. In other words, how much the velocity changes. Okay? That's what we're talking about here. Okay? How much it changes. So, the change in motion that is produced by a net force. Okay? We talked a little bit about net forces in the other podcast, but the idea is that you have a net force. We can abbreviate it like this. Okay? Basically, what we're saying is that if let's say there's an object, okay, and somebody's pushing it that way, it has a net force going that direction. Or let's say you have an object and somebody is pushing it in that direction, but there's a little bit of friction pushing it back in that direction. It has a net force, okay, let's just use a different color here, a net force that's a little bit shorter, but in the bigger direction, okay? It's kind of like this force minus that. So the net force is in that direction. Meaning also that if you have something like that, and you have the exact same force going in opposite directions, there's no net force. These two forces cancel each other out, so there's no net force, which means there's no acceleration. All right, that was a bit much, but what we're saying is that the acceleration of an object, how much its velocity changes, produced by a net force, okay, meaning a force in one direction or another. Now, it is directly proportional to the magnitude of the net force. So here's something to keep in mind. Directly proportional. That means that as the net force gets bigger, the acceleration gets bigger. If the net force gets smaller, the acceleration gets smaller by the same amount. So if you double the force, you double the acceleration. If you have the force, you have the acceleration. If you multiply the force by 10, you accelerate it 10 times faster. All right. Now, again, that's to the, the net force, okay? The magnitude of the net force. It's also in the same direction as the net force, okay? Same direction. So what that's saying is if the force of an object is going to the right, then by all means the acceleration will be to the right. Same thing here. The acceleration will be to the right. Here, the acceleration is 0, okay? In this case right here, because there's no net force, so there's no direction. Okay? If the stronger force was pushing to the left, the acceleration would be to the left. And then this last part here, it's talking about inversely proportional to the mass of the object. Okay? So what we're saying is, let me get that other card, to the mass of the object. What we're saying here is that if the mass of the object goes up, if it's a big mass, okay, big mass, then what will happen is the acceleration will go down. And you know that. I mean, the heavier an object is, the harder it is to get moving, right? And likewise, if the mass is smaller, okay, small mass, you're going to wind up getting a bigger acceleration. It's really actually quite that simple. So a big phrase, but it shows a lot of things. Okay? Now, the acceleration, the amount of velocity change produced by a force, is directly proportional to the magnitude of the net force, is in the same direction as the net force, and is inversely proportional. Now, let's look at this mathematically. What do we get? This is what we get. Okay? The acceleration equals force divided by mass. So, the amount that it accelerates, okay, that's this right here, is directly proportional to the net force, okay? It's proportional to the force. So that's why it's on top. If you were to double the force, okay, you would double the acceleration, because if you multiply this side by 2, you'd have to multiply this side by 2. And also inversely proportional to the mass, okay? The idea here is that if you double the mass, you actually have the acceleration. If you think about it, let's say the acceleration was 4, okay? And let's see, the force was, I don't know, 8, and that would mean the mass would have to be 2, okay? The acceleration equals the force divided by mass. 8 divided by 2 is 4. Now, if you were to double that, if you were to double the mass, now you have, I'll just simplify to one color, now you have 8 divided by 4. What's 8 divided by 4? It's 2. So if you double this, you have this, okay? That's kind of what we're talking about with the math there. All right, now, of course, physicists, we're not going to actually write that out all the time. We're going to do this. We're going to abbreviate it so that acceleration is A, okay? Force is F, okay? And mass is M. So A equals F over M. Put that in your essential equation sheet. Very, 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 very important to put that in your essential equation sheet. Okay? Another way to look at it is F equals MA, and this is actually the one that you're going to see a lot. That's a typical way. This, I honestly don't know why. This tells you more about what the law means, but this is the way people remember it. Okay? I don't know why, but that's just the way it goes. Okay? So really, that's Newton's second law. It's really just saying that the more force you apply on an object, the more it'll accelerate. Okay? And the more massive the object is, the less it will accelerate. That's really what it's saying. There's really not much more to it than that. But let's go. Oops. Yeah, that's really about it. And remember, these guys, this and this is the same equation. It's just algebraically different. Remember, this is more of the acceleration flavor, whereas this is more of the force flavor. In fact, you can even solve it for m and say that m equals, let's see, we have to divide both sides by a. Let's see, if we had F equals ma, we would just divide both sides by a so that the a's cancel out. You're left with m. So m equals F divided by a. Okay? Really, that's it. If you have any questions or you think of any examples where this doesn't happen, let me know. The only other thing that I would say is if you think about, let's say, a bowling ball, okay, standing still, okay, in order to get it moving, you have to apply a force, right? And that application of force would accelerate it. and make it go faster. It would actually have a velocity, okay? So, why do the things slow down though? That's because there's another force acting on it. The reason that bowling balls will eventually slow down is because even though it's moving, there's a slight friction force pushing it backwards. And as it does that, as the friction force does that, it will slow down. Okay? Same force here and here. There's a force pushing it back. And so what you get is that you had to apply a force to accelerate it to get it moving. Now it's moving. It should keep doing that all the rest of its time, except there's friction, which slows it down, over a long period of time until it stops. Okay? I'll see you in class. Make sure you ask me any questions if anything didn't make sense in this.